Welcome back to Mr. Music's Weather Whiteboard. I'm Mr. Music, and again, today we'll be talking about global circulation, one of my favorite topics. Before we dive too far into this, just a quick review because it's important to know and remember that Earth's tilt 23 degrees off a perpendicular axis is one of the primary drivers of Earth's weather. And really the reason of the season is all about the tilt, right? So just for refresher, planet Earth rotates on an axis of about 23 and a half degrees off the axis. And why that's important to remember, during the winter time, the Earth's tilt is away from the sun over here. It's tilting away from the sun. And actually the Earth is actually closer to the sun during this period of time. But because of the vacuum, during the winter solstice, Earth is approximately 91 million miles away from the sun. During the summer solstice, the Earth is actually 94 million miles away from the sun, but it's warmer because the distance traveled has minimal impact because it's basically traveling through a vacuum. It's not absorbing, it's not refracting much of that energy, but yet the tilt is what it's all about. So that time when the Earth is actually closest to the sun, that roughly winter equinox, actually it's called the perihelion, which is going to happen right around January 4th. Perihelion is when the Earth is closest to the sun, very close, but not exactly on the winter solstice. The aphelion, July 4th, when the Earth is farthest away from the sun, yet the tilt towards it makes it warmer. So again, remembering that these direct, and so here's your equator across here. I'll use a different color. The equator and the tropic, or the Arctic Circle and the tropics. So again, you're going to get more direct sunlight here during the winter time. And actually on that winter equinox, you'll get no sunlight above 23. It's actually 66.5 degrees, so it's 23 and a half degrees short of the pole. Another reason why that Arctic Circle is that line of delineation. So you have more intense sun here, direct, indirect, or oblique up here, right? So when you flip this around and the moon is, or the sun is over here, it's going to be directly the opposite. So that seasonal variation, because of the tilt, creates an irregular heating of the northern and southern mid-latitudes and poles throughout that year. But the central tropical regions are always getting a lot of direct sunlight. So that's important to note as we go to the next step, which is called the three-cell model. Okay, so the three-cell model, one of my favorite things on global circulation. So good old planet Earth. In lines of delineation, those 5 parallels, we have the equator, you have the tropics. In the northern, it's the Tropic of Cancer, 23.5. And then you have your Arctic Circle up here at 66.5, which is 23 and a half degrees short of 90 degrees at your pole. So those are rough. So the three-cell model, very commonly used as a model to describe what's happening in our weather globally. And versus using the 23 and the 66, oftentimes it's described more of a theoretical of 0, 30, and 60. So lines delineate, basically cutting each hemisphere into thirds. And it's also good to remember that whatever's happening in the northern hemisphere is happening in the southern hemisphere. And it's a mirror image in the southern hemisphere. All right, so we call it the 3-cell model. There are 3 cells, and their cells are named. The tropical cell is called the Hadley cell. The mid-latitude from 30 to 60 is called the Ferrel cell, F-E-R-E-L. And then the top one from 60 to 90 is called the polar cell, and that should be easy to remember. Okay, so 3 cells, Hadley, Ferrel, polar. So, and again, this is another Hadley cell here, there's a Ferrel cell here, there's a polar cell down here. All right, so things to know. Transition, oh wait, we'll start with this. So Hadley cell, both are going to get a lot of direct insolation, so they are actually the warmest, most volatile, most energetic of the 3 cells. So think about right around the equator is going to get the absolute most energy. And we'll kind of do a little bit of a 3D drawing out here. So what do you see at the poles? At the pole, or at the equators. At the equator, you have, it's warmer there than it is at 30 degrees. So you have rising, hot, moist air. Rising up, gets into the altitude, high enough altitude, starts to move over, comes back down, comes back over. So you get a circulation area looking kind of like this. And you'll have a mirror image in the southern hemisphere. So because both these areas are rising, what does that mean as far as pressure? Well, this is going to be an area of low pressure. And this area is what's called the ITCZ, Intertropical Convergence Zone. And also it can be called the doldrums. And that's roughly from equator to 5 to 10 degrees plus or minus, and depending on the season, this ITZ, if it's the summer season in the northern hemisphere, it's actually a little bit further north. In the summer season of the southern hemisphere or the northern winter, it's a little bit further to the south. So it shifts. It's not pure, hey, it's always right in the equator. Good to know. All right, so when you go up to the Ferrel cell, direct opposite of what's going on in the Hadley cell, you have sinking air here, moving over here, rising up here, dropping down here. So now you have 2 columns on both sides that are sinking air. Sinking air, cooler air coming down. That's going to be an area of high pressure. And then as you can imagine, as we go to the polar cell, again, rising air, moving over, cooling down, dropping down, moving back over. You have that convection cell. So here again, both sides are rising air taking the load off. Again, you're going to be a low pressure system. Now, what's this called? When 2 areas go apart from each other, that's considered an area of divergence. And we'll put a little D there, divergence. As they come together, as in this area over here, this is going to be an area of convergence. So you have rising, divergent, over, down, converging airs like here. So the ITCZ is the area of low pressure. The transition layer between the Hadley and Ferrel is called one of 2 things. It's going to be called your subtropical jet, and also mythical, it's called the horse latitudes. And it's called the horse latitudes back in the early maritime days because of this area, an area of very light winds, and as the story would tell, sailors would try to lighten their loads of their ships, so they'd start throwing things overboard, and they actually would even throw their horses overboard to lighten their load, so hence the horse latitudes. So that transition zone between Hadley and Ferrel, subtropical jet, roughly at 30 degrees, also known as the horse latitudes. As you go up to the next level, the transition layer between the Ferrel and the polar, that's going to be called the subpolar jet. And that's the mid-latitudes that we call most here in the United States. That's our jet stream. And winds that move in the jet stream winds from west to east are called zonal winds. And a zonal wind is a wind that moves along the lines of latitude. Winds that move along the lines of longitude. Think of the prime meridian as a longitudinal line. So they're called meridional winds. So zonal winds move along latitude. Meridional winds around lines of latitude. We'll talk a little bit more about that when we get more into winds. So you need to understand a few things are going on here right now. Again, the transition layers, the primary cells, what the wind's doing at the surface and above. And so lastly, we throw in the Coriolis force. The Coriolis force, because of the spinning of the Earth, will deflect objects not attached to the Earth. In the northern hemisphere, it'll turn things to the right. So objects not attached to the Earth deflect to the right in the northern hemisphere. So what does that mean? So we already know, if we look here, the surface winds of the Hadley cell without the Coriolis force are moving from north to south, like that. But because of the Coriolis force, turning those things to the right, it will bend objects to the right. So it's their right. If you're standing here going this direction, it's turning to the right, turning to the right. And those are called the trade winds. So the primary wind belt within the Hadley cell is called the trade winds. And in the northern hemisphere, they're called the northeast trade winds because they're basically coming more in this direction. And in meteorology terms, we always say the wind is out of, or we determine the wind direction by where it's coming from. So the trade winds, the northeast trades, so the primary wind belt within the Hadley cell, the wind direction is always going to be from the northeast to the southwest. You move up to the Ferrel cell. Primary winds that we see right here, the surface winds normally are moving from south to north. But again, because of the Coriolis force, bending that to the right, so the winds are going to turn this direction. And the Coriolis force also weaker near the equator, stronger nearing the pole. So as you move up this ladder, you'll see a little bit more of a bend. So here the bend is going to be more like this. The wind belt within the Ferrel cell is called the westerlies. We live in the Ferrel cell. We live in the mid-latitudes. The Ferrel cell is the mid-latitudes. We live in the mid-latitudes. So our primary wind belt is the westerlies. That is why if you look at a global weather map of the United States, on average, without those local effects, our weather generally moves, if you think about it, moves from southwest to northeast. So, or they're southwest, so they're coming from the southwest. We call them the westerlies. Lastly, the polar cell, very similar to the Hadley cell. It's coming from north to south, more intense Coriolis force there. So the winds begin to blow this way, and those are called the polar easterlies. So quick review. You have the three-cell model, Hadley, Ferrel, Polar. You have the transition layers between those. The ITCZ, Intertropical Convergence Zone, sometimes known as the doldrums, basically from 0 to about 10 degrees latitudes north and south of the equator. The ITCZ. It is an area of low pressure. The next layer, the subtropical jet, also known as the horse latitudes, roughly at 30 degrees, an area of high pressure. And then lastly, the subpolar jet from roughly about 60 degrees latitude, separating the Ferrel and the polar. Knowing those. So you need to know, then the surface winds, because of the Coriolis force bending things to the right, the primary wind belt, or the wind belt of the Hadley cell, is the northeast trade winds. Of the Ferrel cell, it is the westerlies. And of the polar, it is the polar easterlies. That's the three-cell model. You need to know what the three cells of the three-cell model are. You need to know what the transition layers between each cell are. And you need to know what the primary, or what the wind belt is, and what's driving the wind belt between those three, within those three cells. Got that? Great. This is Mr. Music with his Mr. Music's Weather Whiteboard. Look forward to seeing you back to watch another video very soon.